Okay. We are behind, so we need to get going. All right. So we're going to continue discussing non-deterministic finite state automata, and here is a example of a NFA, right? So what's different between NFAs and DFAs? NFAs have non-deterministic behavior, right? So on a given state, you can, on a given state with a given letter, you can go to multiple places, right? And you can make moves on epsilon. You can just move if you want. If there's an epsilon transition from here, you can just go to D even without seeing any letter of the input, right? So now that's just a mathematical construction. How do we say that what is the behavior of this machine? We think of it as, if I start at the start state, look at all the possible states that the machine can reach on seeing this string, and if any of them is an accepting state, then we say that the machine accepts that string. Okay, so for that we need to understand, I'm just going to do a quick review. So where are all the places from S that I can go on seeing the empty string, right? That's an important concept. Where can I go on seeing an epsilon, right? I could stay in the same state. I could go to D. I could also go to A, right? Because epsilon concatenated with epsilon is epsilon, right? So how do I find that? That's called the epsilon reach of that state. It is simply, if you want to think of it as algorithmically, that's a graph traversal, right? Starting with the state, look at all the states that I can reach just following epsilon transitions only. Okay? So what is this? That is the set SDA, right? Okay, now what about where all can I go from starting with S on seeing a 0, right? Now 0 is not a letter, no, it's a string, right? The string 0, okay? So where can I go? Okay, it's a bit messy now, right? Why is it a bit messy? Oh, okay, look, first, I can start with S and go to all the epsilon places, right? Yeah. Because, okay, and then you say, okay, where all that we already know. So I could be in S, D, or A, and then I can see a 0, and if I have a transition on 0 from any of the states, I can go to all those states, right? Okay, so I could be, after seeing an epsilon, I could be in S, D, or A, and then if I see a 0, where can I be? Okay, if I'm already at S, then I can stay at S, right? And if I'm at A, I can go to B, right? But if I'm at D, there is no transition on 0, so I'll die from there, right? Okay? So now, after seeing the 0, then I have a collection of states, but then I can again make an epsilon move, right? Right? So it's a bit complicated to calculate, but we understand where we can go, right? That's going to be a building block, right? One letter which is interpreted as a string, right? Is that okay? Okay. And then, okay, now the same thing, but if you have a long string, how do you figure that out? Well, you do it inductively, right? First you say, okay, after reading the string 0, where am I? And then from all of those, after reading another 0, where am I? And you take the union and we'll get to all the places I can be after seeing 0, 0. Okay? All right? If any of them is accepting, then the machine accepts that string. Okay? Okay. So why did we define this? Let's get comfortable with the NFA construction. I mean, high level, it's every DFA is an NFA, right? Okay, clearly every DFA is an NFA. So you have at least the power of DFA. So if you want to design something, you can say, okay, I can just design a DFA. But I'm giving you extra power, right, by allowing you all these funky transitions and multiple choices. And that's going to make our life of designing things easier, and you can design things faster and more compactly. Okay, now you say, okay, but that's not a real machine. Why do we care? Well, we'll see that once you design it, we can automatically convert it into a DFA, which will recognize the same language. It's not going to add any power, right, in some sense, but it will make things compact. And that's, see, I mean, if you want to, a faster design or a better design, we want to make our programming language richer, right? So this is what like making a programming language richer, and it makes proofs also easy. Many proofs become easier with this. Okay, and there are many other reasons to worry about non-determinism that are we'll come and see. I mean, we'll see later on in the course as well. Okay, let's see. I don't want to make this. Okay. Okay, did I do something? Okay. Not sure what's happened. Let's see. Okay, all right. So here is an example. Suppose we want to say, this may come up in your searching, right? I want to look at all strings that represent decimal numbers, right? What are decimal numbers, right? Well, it's how do they look, right? First, every integer is fine, and then you have things like, okay, an integer followed by a dot followed by an integer, right? Or I can have an optional, the dot is optional, right? And then maybe minus. I want to indicate whether it's a positive or a negative number, right? So it's complicated to search for that, and I want to recognize all such strings, right, which are valid decimal numbers. So I mean, NFAs, you can write a DFA for that. It's not too hard, but NFAs make life a little easier, okay, in compactly representing that. So here is how one way of doing it. So this is a start state, and you say, okay, maybe it has a minus in front of it, right? But it's optional, right? A minus in front is not necessary. So we give it an option. You can either move here, either on seeing an epsilon, which means that there's no minus, or you see a minus, okay? And then you come here, and you say, okay, now I see some integer, and then followed by a dot, followed by some integer. That's what we want to think of, right? Okay, so what we don't want is, so what is this branch? This branch says basically that I don't want things like 0 point something. Okay, that's not a valid thing. I mean, you may allow that, but this NFA is not allowing 0 point 0, right? Because that's redundant, right? So we want to allow only, for whatever reason, that's our choice, that if you have a 0 in front of the dot, a single 0 is the only thing that is allowed, right? So you say, okay, you can allow a single 0 followed by a dot followed by an integer, right? And or if you have to have more than you have an integer, you need to start with something which is not 0, and then you can have any number of digits then followed by a dot. That's also allowed. Okay, so you can see that this expression or this machine is a very compact way of representing what we want, right? Choice is automatically allowed, right? And it's non-deterministic, so it makes design easy, right? If you had to write a DFA, you have to worry about all the cases, right? Because it's a proper machine, you have to worry about all the edge cases, you have to worry about how to make the choices very carefully, right? Because and that's difficult to design, right? While NFA makes life a little easy, right? And so that's why it's a nice language, right? Okay, so just to get going, right? What about let's try this, right? I want all strings that have CS374 as a substring. Okay. All right. So how are we going to do this? Okay. So here is a very simple way of doing it, right? You know, we start, right, and C S 3. Okay. This is an NFA which recognizes all strings which have CS374. Okay. Let's see why is that. Okay. So what is this machine allowing us to do? We wait on this state. Now, what does a string which has CS374 as a substring look like? Right? It has some stuff, then CS374 and some stuff. Right? Yeah. Agreed? All right. So, yeah. I will be here. You see, that's the power of NFA. It allows us to guess when we should go into CS374. Okay. Okay. Yeah. Yeah, but yeah, exactly. See, this is the thing. The definition of NFA is like, when is a string accepted by an NFA, right? It's not a deterministic machine, right? Its behavior is not fixed. Okay. The only thing we need to verify is that is every string which contains CS374 accepted by this machine according to the rules of the game. What are the rules of the game? The rules of the game are that if there is an accepting path, then the string is accepting. But there could be multiple ways of doing it, right? Yeah. Oh, sorry. Yes, the accepting state. Yeah, good observation. Yeah, that is the single accepting state. Okay. Yeah. Question. Yeah. So what does this mean? I can't hear you, so you need to speak louder. Sorry. Oh, so no, this is sigma. That means that, sorry, this sigma means that any letter in sigma. Sorry, that's what it means. It's a compact wave, right? Yeah. Sorry. No, sigma doesn't have epsilon ever. No. Okay. Okay. So let's this is a let's look at the string blah CS374 blah. Okay. Why is it accepted by this machine? Okay. So while I'm reading blah, I stay here. Okay. And then when I see CS374, I go and then I stay here and do blah. Okay. So I'm showing you that, sorry, that's also sigma, right? So I can read whatever I want. No, okay. Here, let's see. That this is why CS37 blah CS374 blah. Okay. I will read all this here and then only move here. Okay. See, that's the power of non-determinism, right? I magically move. Okay. Okay. What does it mean magically move? It just, the machine is not real, right? How does the machine know? It's not a real machine. It doesn't know. It's just a mathematical construction. Okay. What is the definition of this? Is the string accepted by the rules of the game? Okay, that's all we need to know. Okay, it's just a idealized construct. It's just a definition, and we have to get used to it to see why it's interesting and powerful. Okay, yeah. Oh, it's not accepted. Show me how that will be accepted by this. You'll get, remember, if there is no transition out of this, then it dies, no? Yeah, that's the thing, definition, right? So what is, so the whole game is to properly understand what it means for this machine to accept a string, okay? For this machine to accept a string, you have to show me a path from the start state following these things so that it reads the string properly, right? No, okay, so the two things. I'm not, what do you mean? I'm not asking you to die, right? Okay, so what I'm saying is that, okay, all I want you to understand till you get used to it is, this machine will accept every string which has CS374 in it as a substring, and only those strings. Okay, so let me first convince you that it accepts every string which has CS374 in it. Is that okay? Okay, so what does a string which has CS374 look like? It has some prefix, CS374, and then some suffix, right? Okay, I claim that I can stay in the first state as long as that prefix is there, because I'm allowed to stay there, right? And then as soon as I see the first 374, I walk through this thing till the final state, and then I'll read the suffix there. So I'm showing you why, according to the rules of this game, this machine will accept the string. Yeah? No, I mean, but then you don't understand the rules of the game then, of what this machine's behavior is. When does it accept a string? Yeah, because I can read CS37 blah all the way here. I'm allowed to read this, right? Because remember, the sigma, every letter is allowed here.
Oh, but maybe you got to specifically search. You got to find which C you want to look for.
I am not doing anything. That's the definition. It is a mathematical definition of what this machine is supposed to accept, right? Okay, what is the meaning of this machine accepting a string? I told you, if there's any path from the start state while reading this and takes you to the accept state, there are multiple choices, right? Okay? Okay. Yeah, that is, yeah, you could be in both at the start state. Yeah. Yes. Okay. Okay. It's a different, yeah, makes sense. Yeah. Okay. Now, the thing is, you have to convince yourself, which is a little bit more work, that if you get all the way here, the string must have CS374, right? Because how did I get from here to here without reading CS374? There's no way of going from here to here, right? Yeah? Okay. One more question before I move. No, you cannot use the same machine to say which strings do not contain CS374. No, complementation is very hard. No, it is not true, right? Because this machine is non-deterministic, you cannot do that, okay? We'll come back to that. Let's get used to that. Okay, this is the important thing. See, I want a thing that contains either CS374 or CS473. Or, right? Remember, or. Okay, here is what I do, okay? So what I can do is I can stay here and then make an epsilon move and then read, well, I mean, okay. Okay, 1 second. I'll make it a little bit more compact, though you don't have to think like that. Okay, so here is a start state. We keep reading symbols, and then we see C, then we see S. Okay, and then we go on epsilon. Okay, it is slow. Okay, and okay, these epsilons and sigmas are a little confusing. Okay, all right. Okay, is that okay? All right. C. Okay, we keep. So remember, it's or, right? I'm okay as long as it is either CS374 or CS473, right? So I keep reading. Then when I see CS, I can go here, right? And then I can either go to 374 and oh, so accepting state is the last one. Okay. Or I can go to 473 and go there. Okay.
Can you combine three and four questions and say,
You have to be careful, right?
four,
I don't want to think like that because it's already, you want to be as simple as possible to get your task done without trying to, right, minimize it, right? You want to make sure that you're not confusing yourself, right? See, that is the power of NFA. DFAs don't give you that flexibility, right? Because it's deterministic. If you have to do 374 and 473, you have to keep track. What did I see so far? Oh, did I see CS? Okay, 3 no, okay, right? You know, you have to worry about exactly what you have seen, right? Here, I can non-deterministically guess. I can wait till I see CS, and then I can, yeah, I can go here, right? Okay, yeah? Any questions on that? Yeah. Yeah, because I had a branch, you know. Yeah, I could do that too. But I liked it this way. Okay, you'll see why it's nice to use epsilons. Yeah. See, there are many variations of this possible, right? But I just want us to get used to the idea that this will work, right? Okay, I'm not saying it's the only one, right? You know, so branching is important. Okay, let me do one more. Okay, and okay, and is a little complicated operation for NFAs. Okay, remember DFAs. How did we do and? Sorry. No, if I said, you know, I want and is intersection, right? Okay, how did we do intersection with DFAs? No. Okay, it was complicated, right? We designed a DFA for accepting CS374. We designed a DFA for accepting CS473, and then we had to do the product construction. Yeah, because we have to simulate intersection, right? That's complicated. So we can do this because we know how to do a DFA for CS374 and we have a DFA for 473, we can do it too, right? But for NFAs, it's a little complicated. Intersection is not easy for NFAs, right? Okay, until we see that we can convert to DFAs. But I just wanted to think as a string problem. When does a string have CS374 and CS473 and? Okay, just for you can do it with DFAs too. It has that. There are two possibilities that CS374 comes before CS473 or CS473 comes before CS374. Okay, but can you do the first one? I just tell you I want a string to have both CS374 and CS473, but I want the 374 to come before 473. I mean, one 370, I mean, there could be multiple copies. Yeah, how will you do that with the NFA we designed? So we can take this thing, okay, I'm not going to draw it because it takes a while. You wait, you see CS374, you wait, then you see CS473, and then you're done. Yeah? Okay, but now it may be that I can have 473 come before 374, right? So then that also you can design an NFA, right? Because then you first wait, see CS473, wait, then you see CS374, and then you're done. Yeah? But now I'm allowing you either this or that. Okay? So then you have you branch. At the very beginning you say I can either go this way, which means I am going to verify all strings which have 374 before 473, and now I go this way, I am verifying all strings which have 473 before 374. Okay? It's a bit messy to actually write all that down, but conceptually it's very easy, right? Okay? Because I'm allowing you OR operation. So that's nice. Okay, one last example before we do some more theory. Okay, this is a very interesting language which we'll come back to later. So LK is all bit strings, that means the alphabet is 0, 1, that have a 1K positions from the end. Okay, so what are the strings, right? That means that, so K, let's take K equal to 3. What does that mean? What is K equal to? Let's fix K equal to 3. This light's dancing around. K equal to 3. It means all strings which have a 3 positions from the end. Right? So that means anything which is less than 3 positions, less than length 3, we won't accept, right? So what is a string which I have something like 1, 0, 0, but I can have any string before this, right? Yeah, or I can have any string before this and 1, 0, 1, 1, 1, 1, 1, 1, 0, and those are the things, right? Okay, so for K equal to 10, you will have what? You have anything followed by 1 followed by all possibilities, right? Okay, I want to write an NFA for this. From the end, yeah, that's why it's a bit of a pain, right? So if you had to write a DFA, what would you do? No, because it's not the same language, no? This is what I want.
I mean, yeah, but you know how many parts.
But I am not allowed to flip the string. I only can read it from left to right, no? Yeah. Okay, if you had to write a DFA, what would you do for this? What do you need to remember? No, I can't remember that because I could have a long string, right? Yeah. So how will you design a DFA for this language? K equal to 3. You've already forgotten DFAs, right? What do you need to remember? No. Remember, all these are allowed, right? What is not allowed? What string is not allowed? I can't have this, right? That's not allowed. Okay? I can't have any string and this is not allowed, right? Why? Because there is a 0 in the 3 positions from the end, right? So any string which has 0 followed by 2 other characters is not allowed, right? No, K equal to 3 here, right? Yeah, K equal to 3, right? Fix K equal to 3, okay? Okay, let me make it 3 just to make you, okay. No, I mean, LK is interesting, but let's fix 3 to fun. Well, okay, I can do this by if I remember, I mean, DFA is like this, right? I can remember the last 3, I have a state for, if I remember the last 3 parts of the string, I can do the job, right? I just remember all the last 3 things I've seen so far. Okay, but how many possibilities are there for this? If I have 3, I have to remember what? 8, right? My state space is going to have 8 states. The state space is going to be 0, 0, 0 if the last things that I've seen are 0, 0, 0, right? Is that okay? DFA. Okay, but if I have K, how many things do I have to remember? 2 to the power K, right? Because I have to remember all the last K things I've seen, right? Aha, NFA will allow us to do it with K states. Okay. Why? Can somebody design an NFA for this? Okay, here is how you do it for 3, right? Yeah, you can do it with the DFA. Yeah. But you require 2 to the K states because you have to remember all the last K things I've seen, right? Okay, but this one, I can do this, right? 1 and no. This is an accept state 0. Okay, is good. So what do? I keep reading. Then I see a 1. Then I see 2 characters and I'm done. I cannot see anything else. Sorry? Oh, this is for 3. Okay, if it is K, what do I get? How many states do I need? I keep reading and I see a 1, I go to start state, Q, this is a K, how many do I need? K minus 1, K minus 2, okay, and so, okay, 0, 1, 0, 1, okay. So with K states I can get away with it, right? Why? I read till I detect the 1 in the kth position. I am guessing that the string is going to end, right? And then I jump with 1 and then I have to read only K minus 1 more letters and I have to reach the final state. Yeah? 2 to the K states. No. You cannot do it. We'll prove later on that you need 2 to the K states in any DFA that recognizes this language. Okay, it's not obvious maybe, but you cannot do it with 2 K states. Okay, do you see that, right? That with an NFA with K states you can get away with it, right? Yeah. What is the NFA doing? It's waiting till it is guessing, right? It's as if it knows what to do, right? But that's just one way of interpreting it. But it's like just we are ensuring that. So what NFA gives us is that it allows us to verify. The NFA allows us to verify that a string is in the language. It doesn't do the job for us, okay? Because it's not a real machine. Okay, so NFAs are good that way. All right. Okay. Here is a simple technical thing that we'll use, which says that without loss of generality, you can assume that your NFA has a single final state. Why is that? Okay, if I give you an NFA, something complicated, I claim I can change it to another NFA, so there's only one final state. I don't need more than one final state. Yeah. Exactly, right? So I have some arbitrary NFA. I don't know how it looks like. It has a start state. It could also be a final state. And there are many final states, right? This is my NFA N. I have no idea what it does, right? Okay. But I claim I can transform it like this, right? I create a new final state, put an epsilon transition from all these guys, and then I make sure that these guys are no longer final states. Okay. Okay. So I had an old NFA. I don't like it NFA because it has too many accepting states. It's not good for my proofs because right? I want it to have only one final state. What will I do? I create a new NFA, which is the same old NFA. I add one extra final state, new state, and make that the single final state. And all the old final states have an epsilon transition to the new final state. Okay. Sorry? No, this is epsilon. No, sigma won't work. Okay. Yeah. So remember, you want to claim that this machine accepts a string if and only if the old machine accepts the string, right? Okay. Yeah. Yeah. A question. Yeah, you can make it. Yeah, you want to make the start state different from the final state. Okay, it's just for the proofs. It's just for simplicity, and it's also to see that you can get away with it. Yeah. Any questions on this construction? Seems intuitive. Yeah. Okay. Okay. All right. Now let's do something, right? Okay. So we want to know, right? We want to we like closure properties because we can do interesting things, right? So we can ask the following question. Are the languages accepted by NFAs closed under union? What does it mean? If I have an NFA which accepts L1 and I have an NFA which accepts L2, is there an NFA which accepts L1 union L2, right? Okay. What about intersection? What about concatenation and clean star and complement, right? These are simple operations that we would like. Oh, I design an NFA for this language. Can I design an NFA for the complement of the language, right? For DFAs, it depends. So regular expressions are closed under union by definition, right? But intersection is not obvious, right? For regular expression, intersection is not a natural operation, right? What about DFAs? Well, DFAs intersection, we showed that it is closed under intersection by using what? The product construction, right? So that was nice. And we also showed that DFAs are closed under complement, right? But it is not easy to see that regular expressions are closed under complement, right? It's hard to design a regular expression for the knot of something, right? We don't know how to do it. It's a pain. Well, the regular expressions are closed under clean star, right? While it is not obvious that DFA languages are closed under clean star, right? And concatenation. What was hard for DFAs? DFAs concatenation is hard, right? If you think about it, if I say, I have a DFA for L1 and I have a DFA for L2, is there a DFA for L1 concatenation with L2? It's not a natural operation for DFAs. I mean, we haven't discussed it, but it's not a natural operation, right? Okay, so now with NFAs, we can ask the same questions, and some of this will be easy and some of this won't be easy. Let's see what are the easy ones. Okay. First, I claim union is very easy. That, if I have a NFA for L1 and an NFA for L2, I can easily create an NFA for L1 union L2. Why is that? No, so here I have an NFA for N1 for which accepts L1. I have an NFA which accepts L2. How can I create an NFA which accepts the union of these two languages? What does it mean, union? I should accept a string if it is either accepted by this machine or this machine, right? It's an OR. So how do I create a new machine which accepts this or that? No, DFA we don't. For union, how did we do with DFAs? But the NFAs are tricky. You can't do product construction. But it's much easier. Okay, yeah. Yeah, so it's much easier because you can do a branching. This is an epsilon, not sigma, okay? Okay, and that's it. Yeah? Yeah, go epsilon, right? Okay, so it's so simple, right? With union, it's so simple, right? Yeah? Okay, if you want, we can add one single final state also if you want that, right? Okay, great. Union is very easy for NFAs. What about concatenation? The power of epsilon is again going to come into picture. So it's a clue. What should we do? So we have one NFA which accepts L1, which another NFA which accepts L2. What does it mean that we want to accept the concatenation? That means that, we want to accept strings of the form W1, W2, where W1 is accepted by the first machine and W2 is accepted by the second machine. Okay? Yeah, so what you do is you just do this. Okay, so this becomes your start state. We add a transition from this final state. Remember, without loss of generality, we can assume our NFA has a single final state, right? Without loss of generality, we can assume our NFA has a single final state. Otherwise, we could add one more final state. This is where we use it in the proof. Okay, remember, we said, if you had more than one final state, what do? We just create one more final state, right? So without loss of generality, we can assume our NFA has single final state. Okay, it's convenient for the proof. There is nothing deep going on here. It's just convenient for the proof. You can assume that it's only single final state, right? So we just this is our new machine which I claim accepts precisely the language L1 concatenated with L2. Yeah? Why? Okay, if there is a string W1, W2 where W1 belongs to L1 and W2 belongs to L2, how does this machine accept it? Well, it starts here. What does it mean that W1 is accepted by L1? It must take you from Q1 to F1, right? Okay, and then you transition to this, and this guy must accept W2, so it will take you from Q2 to F2. Yeah, yeah. So, but when we concatenate languages, we want to accept all strings of the form where W1 belongs to the first language and W2 belongs to the second language. Yeah, but non-deterministically it will guess, and yes. Yeah, we don't know what W1, W2 is, right? I'm not giving you the breakup. We have to accept all strings which can be written as W1, W2, where W1 belongs to L1 and W2 belongs to L2. Yeah? It's like just concatenating two regular expressions, no? Yeah? Good enough. Okay, very good. Okay. What about clean star? Okay. So I have a machine which accepts a language. Now I want to accept all possible concatenations, right? That's what clean star means, right? That means I can go. So I have a machine which accepts L, N1 is accepts L. I want to accept L1 star. What is L1 star? What is L1 star? L1 to the 0 union L1 to the 1, L1 to the, so let's say call it L, right? L to the 0 is epsilon, okay. L to the k is k concatenation k times, right? And so we want to accept all possible concatenations. Yeah. Loop back is good, okay. Epsilon, not sigma star, right? Because I want to go here and then come back to the start state, go again, right? Okay. So, okay, this seems to be the natural first idea, right? So we put a loop, sorry, it doesn't work, okay. What can I do? Okay, it's all, okay. So one natural idea is that we put an epsilon transition from the final state to the start state and say that we'll make this initial state also an accepting state. Why should we make that initial state an accepting state? Why is that useful? Because we have to accept epsilon, right? As soon as we see, we have to accept epsilon, right? Because L star contains epsilon, right? Okay, this doesn't quite work. Why? Yeah, making the start state a accepting state is dangerous, right? Because we are now maybe accepting strings which are not there in the original L itself. Okay? So we are a little careful, right? We can't just do this, but the following modification works. We are a little bit careful, right? You know, we pull ourselves back, we add a new start state, okay, so that we don't disturb the old machine, okay, and put an epsilon transition to the new start state and make this a final state, but this guy only goes with an epsilon to Q1. The interesting thing about this guy is that there is no way for somebody from here to go directly to this guy. Okay. Okay, this is not a bad idea, but it has a subtle bug. Okay, all right. To avoid that, you have to do this. Okay. Now, I can sit here and spend 10 minutes explaining why this one works and the previous one doesn't work, but it is beneficial for you if you to go back and say, create a concrete example of why this will fail and why you can argue for yourself that this will work. So what does it mean that this works? You have to argue that any string in L star is accepted by this machine and that anything that this machine accepts is in L star. Okay, you have to go both directions. If you never do the exercise, you won't understand its construction. Okay, why does this work? Why does the previous one not work? Okay, all right. It's not hard, but you have to spend a little bit of time. Okay, okay. So I won't. Yeah. Maybe no, because you can't allow epsilon transitions. No. You have to be careful. It's not natural. Okay. No, it's not clear to me. I mean, maybe it's possible, but you have to be very careful. Okay, right? It's not obvious. Okay, NFAs make it very easy, right? Okay, clear. So NFAs are closed under what? The languages accepted by NFAs are closed under union, concatenation, and star, right? Intersection we don't know because product construction is very, very tricky with NFAs. Okay, we don't know how to do product construction with NFAs. Okay, but then already we get some interesting feature that all regular expressions can be captured by NFAs. Okay, why is that? Intuitively, why is that? Okay, what does it mean? It means that any regular language is captured by an NFA. There is, for every regular language, there is an NFA that accepts that regular language. Let's review what regular languages are. What are regular languages? We start with three base cases, right? Empty set is a regular language. The language containing just epsilon is a regular language. For every letter in this alphabet that language containing just that string is a regular language. And then we allow unions, concatenations, and what? Clean star, right? And then we have a notation for regular expressions, which is just the same as the definition of the this operation, right? Now I claim that every regular language can be accepted by an NFA, or for every regular language there is an NFA that accepts it. So why is that? Intuitively, why is that? What have we done so far that will convince you that this is true? Yeah. I didn't prove it directly. What I did prove is that NFAs themselves are closed under union, right? NFAs are closed under union, they're closed under concatenation, they're closed under clean star. So if I verify the base cases, you should be done. Okay? Okay, let me do it slowly. Okay? Okay. So first, we'll do, okay, so let's do it this way, right? The theorem is that for every regular language L, there is an NFA N that accepts that language. Okay. What is the proof strategy? Like everything here, for every regular expression R, show that there is an NFA N such that the language accepted by the regular expression is the same as the language accepted by the NFA. Okay, induction is on the length of the regular expression, right? How did we create the regular expression, right? Okay, well, what are the base cases? Well, we stated the base cases for regular expressions are the empty set, epsilon, regular languages are this, and A for in the sigma. How can we create an NFA which accepts the empty set? What is an NFA which accepts the empty set? I want an NFA which accepts the empty set. What does that mean, accepts the empty set? That means its language is the empty set. What does it mean? That it shouldn't say accept any language, right? It's any string. So I want an NFA such that it doesn't accept any strings. Nothing okay, that it has to have a start state, right? I'm sorry, but you have to have a start state. Okay, okay. So this is fine, no? Okay. So if you want, we insist that we want a final state, we can put this, right? Yeah. This accepts the language empty set, right? Okay. What about epsilon? It's like a DFA, no? What is right? What is a NFA which just accepts epsilon, the string epsilon, nothing else? Yeah, you can. If I want, I want a nice construction, I can do this, right? Epsilon, right? I want always a start state and a final state which are separate. I can do this, right? Yeah. Okay. What about a single letter? It's the same thing, right? You put A. Yeah? Agreed? Okay, so base cases are done. Once base cases are done, we are done. If R1 and R2 are regular expressions, by induction, we already have an NFA which accepts the language of R1 and an NFA which accepts our language of R2. And we now want to have to accept what? L of R1 union L of R2, right? But we already saw that NFA, if I have an NFA which accepts some language and another NFA which accepts another language, the union is just by, we already saw that how to do that, right? So we can create an NFA which accepts that, right? Yeah? So we just basically, what we saw already gives us all the inductive cases, right? Concatenation we already saw, right? If I have an NFA which accepts one language and another NFA which accepts the language, we can do the concatenation. So, and clean star we also saw. So the induction keeps going through because we already verified all these three nice properties. Yeah? Okay. So we have to verify the base cases. Okay, now here is an example to make it more concrete. So here is something you may want to do. Here is a regular expression. Create an NFA which accepts this language. Okay? Okay? How do we do the NFA for which accepts this language? So remember, this regular expression is this concatenated with this, right? So, okay, we have a box which should accept this language, and we have to concatenate it with this box, right? Well, okay. And okay, what is this box? Well, it is an union, right? Okay, so remember that we have to split this like this. And this guy is also but remember, this is a star first, right? It's a star of this expression, right? So you need this star construction for that, right? And then we expand, right? We say, this we expand as, what is this? This is a base case, right? Yeah, epsilon, this is a single thing, so we already figured out how to create an NFA for the base cases. So we expand that, and what is this? This is now inside the box. It is what? It's a union. Yeah. So we have a union box, right? And what is the inside this box? The union is again a concatenation, right? So we okay. It's boring, but you can see the process, right? So you'll get something after you do a simplification. You'll get a nice simple NFA. Okay, it's sorry. Yeah, it works. I mean, this is not following the algorithm exactly, because then it will become like this long NFA, right? You can simplify a little bit. Okay, it's purely mechanical, right? Once you know this simple, basic, high-level operations, it's a purely mechanical procedure. Okay. Any question on the fact that NFAs are this very nice beasts which allow us to do unions, concatenations, and star? Yeah. Oh, so in each of these constructions we had the union and all this, we had the right final states, right? Yeah. But how did I, so wait, you have to be careful, okay. How did I figure out what is the accepting states in this construction? This is the only accepting state, because I removed this as the accepting state. You start with two NFAs, they have their own accepting states, right? When you put them together, you have to be careful. See, let's do the union, right? What are the accepting states of this? The accepting states of this and the accepting states of this. Okay. So while we are doing these operations, we have to be careful about what the accepting states of the resulting machine are. So here, these are the accepting states of this machine. When we did this, only this is the accepting state. I had to remove this, otherwise the construction is not correct. Right? So each of this union, concatenation, and clean star, we have to figure out what is the right construction, and that involves knowing what the accepting states are. Okay? It's not later on. We do it in each of the operations. Okay? So here too, the accepting states are precisely this single one, because we started with a single accepting state, and this one now. Okay? There are only two. Okay? So that's important for the construction. Okay? Questions? Yeah? Yeah. Yes. Oh, that's because I simplified it. It's not a mechanical algorithm, because that will become very long, so I simplified it. That's not the result of following the algorithm very precisely. It's a little simplified. Okay? Yeah, be careful with that simplification. Okay. Yeah. Any other questions? Okay. Okay. So hopefully we have a better sense that NFAs are very good design languages. They allow us to write compact machines. Now what's the point of all this? Great, you created this artificial machine and now you are playing games with it, right? So clearly we're not wasting your time, right? You're paying good tuition, we have to give value for money, right? So there's a method to this madness, right? The method is that, that there is a reason why people spend time on non-determinism, that here is the reason, that you can actually convert every NFA into a DFA. Okay, so they're no more powerful than DFAs, except that they're giving you a more powerful language to express your thoughts, right? That's the idea. Okay. No, empty state, empty set. Okay. So here is the thing, right? It's a matter of vocabulary. This machine accepts the empty set, the language empty set. Okay. What does it mean? It means that it accepts no strings. Okay. There's a difference between language and strings, right? A machine accepting a language is it's overloaded. I'm sorry, but it's historical. Okay. When I say a machine accepts a language, what does it mean? That means it only accepts strings in the language and nothing else. Okay. So accept is overloaded. Machine accepting a string is different from machine accepting a language. Okay. So you have to be a little careful, right? We use the word accept for both language and strings, right? So accepting a string means that on that string the machine is taking you from the start state to a final state. That's what the definition is, right? When you say this accepts the language, it means that only strings on the language are accepted by the machine and nothing else. Okay? So the language versus string sometimes is confusing, okay? You have to know, am I talking about language or am I talking about string, okay? Okay, so now we are going to do the following, okay? Okay, so here is the theorem we want to prove, okay? We want to prove that all the three definitions of the things we have discussed so far, regular languages, languages accepted by DFAs, and languages accepted by NFAs are exactly the same set of languages. They are not different, okay? So how do we prove this? Because we have defined three things, right? Regular languages were defined using this union, concatenations, clean star with base cases. DFAs were defined in one way, and NFAs were defined in another way, right? Okay, what are some easy directions? Obviously, every DFA is an NFA, right? So they are going to, if a language is accepted by a DFA, then obviously there's an NFA also which accepts that language, right? So they are only going to be smaller set of languages, okay? We just saw that NFAs accept all regular languages, right? Yeah. So they are at least as powerful as regular languages. We don't know the relationship between regular languages and DFAs, right? It's not so obvious, right? Okay. What we're going to show is that DFAs are as powerful as NFAs. NFAs don't buy you really any more power, okay? So once you do that, what does it mean? That means NFAs and DFAs are the same, right? In terms of accepting language, right? The same class of languages. But that means that because we already saw NFAs accept regular expressions, DFAs also can accept regular expressions, right? How do you do that? First, we already saw how NFAs accept a regular expression, and then you use that NFA and make a DFA, and now that DFA will accept the regular expression. Okay, finally, we have to understand, are regular expressions as powerful as DFAs and NFAs? Okay, that's not obvious, right? Can regular expressions accept everything that DFAs and NFAs do? Yes, we can prove that too, that regular expressions can accept all languages accepted by NFAs and DFAs. But that is the last direction, which is a bit more technical and painful. We will not do it till we do algorithms, okay? Because the algorithmic procedure to properly understand the proof of that requires understanding a shortest path algorithm in graphs, okay? So we're going to postpone because I can explain the algorithm to you, but it looks somewhat intuitive, but I cannot prove that it's correct. So, but we'll prove it later, okay? So they're all the same, right? They're all powerful ways of understanding. Okay, this is the hard part. For every NFA N, I can create a DFA such that it accepts the same language. We are going the hard direction now, right? Because NFAs look more powerful, but I'm saying no, I can create a DFA which will accept the same language. So how are we going to do this, right? So let's go back and say, okay, how do we design a DFA for a language at all, right? When we designed a DFA for a language, how did we figure it out? What does if DFA has to recognize a language, what should it have, right? DFA has a limited memory, right? Yeah? It can't remember much, right? Okay, but what is the language we are trying to recognize here? It's a bit abstract because it's not like, it's all strings which end in 0, 1. It is the set of all strings that this fixed NFA is accepting, right? And I want to accept the same strings, but my machine should be a DFA, right? Okay, so we'll come back to this. So think of a design principle for DFA, right? What should the DFA remember, right? The DFA, after it sees a portion of the string, it has to store enough information so that, it can accept it or not accept it based on whether it's in the language or not, right? But what strings are we trying to accept? I have a fixed NFA N, right? What string should this machine accept? My DFA should accept only those strings that this n should accept, right? Okay, then we have to understand, when does n accept a string? When does NFA accept a string? It accepts a string if and only if that NFA from the start state takes that string to some accepting state. Right? There could be many possibilities, right? Okay. So what should the DFA remember when it sees a prefix of a string? What should it remember so that it can say, would NFA actually accept this string? What should it remember? Okay, yeah, so but how does it know, right? Yeah, but it can be in many states, no? Right? Okay, so I want to claim to you that it needs to remember what are all the possible states this NFA could be after seeing this current string. Okay, suppose it remembered that, right? That's not a lot of information, right? That is a fair, because remember n is fixed, right? The machine is fixed, n is fixed, right? The string is long, right? I saw a long string so far, right? But my DFA is seeing a long string. It cannot remember the string, right? But it wants to know what would the NFA have done on this string, right? What is the key information it needs to remember? It only needs to remember where are all the states that this NFA could be after seeing this string. Okay? That is enough, I claim. Okay? So I saw a long string. I don't have to remember the string. I am fine remembering only the set of states that the NFA could potentially be in after seeing this long string, right? Okay, is that clear, or is that somewhat okay? Okay, so my DFA is trying to figure out, will this fixed NFA accept this string or not, right? Well, it's bizarre, but it just keeps track of only the set of states that this NFA could reach after reading that string. Okay. And that's all it needs. Okay, if it has that, is it sufficient? And I claim it is sufficient because after I see a prefix of the string, I see one more letter. What should I remember now? I need to remember what are all the states that the NFA could be after seeing this one more letter, right? Okay, but I only know what it could have been at the previous step. But I claim that is enough to figure out after seeing one more letter where it could be after seeing that one more letter. Why? Because it can keep n also in its memory, right? You can compute, oh wait, the NFA could have been in all these potential states after seeing the string x. Now I saw string x followed by a. Where could the NFA be? I don't need to know where all it has been. From the current set of states the NFA had reached, seeing one more letter, I can compute from the NFA where all it could have been after seeing this one more letter, right? So I'm maintaining that information properly again. At the end, when the string ends, how do we know whether we should accept that string or not? Oh, NFA could have been in any one of the states. I know all the states. If any one of them is accepting, I should accept. If none of them are accepting, I shouldn't accept. Okay? So I'm simulating the behavior of the NFA by just remembering what are all the possible states it could be in after reading this prefix. Okay? If I can keep track of that information, then I can update that information when I see one more letter, and then I keep going. Okay? Yeah, and the behavior of the machine n. Okay? Okay, so formally, what should the state space of my DFA be? What I need to remember, right? What do I need to remember? The set of states that the NFA could be in. Okay, so it means it's the power set of the states of Q of the NFA. Okay, that means I have to know, for every possible subset of the states the NFA could be in, I have to have a state. So I have a huge state space. How big? Exponential in the state space of the NFA. If the NFA has 10 states, I have to remember my state space is 2 to the 10. Okay. Suppose NFA has 10 states, right? Okay. No, I need to know all possible states, right, that the NFA could be on seeing the prefix, because if I didn't know that information, I would not know after seeing the next letter whether I would have be able to go to an accepting state, right? If I don't remember all the possible states I could be in after seeing the prefix, but only remember the accepting states, how will I know after seeing one more letter where else I could be, right? Maybe so far I could not be accepted, but one more letter later I could be accepted, right? But I can't just remember what are the accepting states. I have to remember all the possible states I could be after reading the prefix. Okay? So that is my state space, and so this is the formal construction. So the NFA has states Q, sigma, start state, delta, accepting states. Now we create a DFA. Remember, this is NFA, DFA. Very important to keep this. So what are my state space? Q prime, alphabet is obviously the same, delta prime, S prime, A prime. I have to tell you what my state space is and all that stuff, right? So my state space is the power set of Q. Okay, how many are there? 2 to the number of states of the NFA. Huge state space, right? Okay. What is my start state should be? Okay. What are we trying to simulate, right? Remember, we are trying to simulate what the NFA would be after seeing no string. The start state means that the DFA, where will the DFA be in the start state? On epsilon, it should remember what the NFA could be in epsilon. Where could the NFA be on epsilon? The reach of its start state, right? So the DFA start state is the epsilon reach of the NFA start state. Okay? Okay? What should be the accepting states? Remember, the DFA state is a subset of the NFA states, right? What is the meaning of that? It means that the NFA could have reached that set of states starting with the start state, right? So if any of them contains an accepting state, I should accept, right? That is the definition of what NFA will do, right? So my accepting state should be any subset of the states where it has a non-empty intersection with the NFA's accepting state. Okay? Okay? So, and then the delta is the tricky part, okay? This is a painful thing, but it is intuitive. So what is this saying, right? It's a lot of math, but what is the meaning of x comma a? Remember, this is the transition function of my DFA, right? Okay, so no. So this x is a set. So think of this as Q1, Q2, Qk. Okay, so what does this mean? That means the DFA is in this state, right? Okay. See, if the DFA is in the state and it seeds a letter, what does it mean? It means that we want to know if the NFA could have reached any of these states and it sees a letter, where could the NFA go to? That's what the DFA is trying to simulate, right? Okay? Okay. So if the NFA could have been in any one of the states after seeing a letter A, where could it be? Yeah? Yes, yeah, I'll say why there's a clean star. It's a bit subtle. Let's understand this. If the NFA was in any one of the states and it saw a letter A, where could it go? Let's say it is in one state Q1 and it saw a letter A, where could it go? It can go, I mean, A could have, on A it can go to multiple states, right? But it can also go on epsilons, no? Okay, it could go on epsilons, it can take a transition on A and it can again go on epsilons, right? That's the only thing this is capturing. It is saying that look at all the states in that set X. From that set Q, from that state Q, look at all the potential states it can go on the string A, not the letter A, but the string A. Okay, to use string I need delta star, not delta. Okay. All right. So what I'm saying is that if I'm in NFA is in state Q, it sees the next letter. Where can it go? It can go to many places. But what are those places? It can make epsilon moves, take A, and then more epsilon moves. No. So what are those things? By definition, that is delta star QA, because I'm interpreting A not as a letter but as a string. Okay. So I take the union of over all those, and that's the right thing, right? Because I could be in any one of those potential places, right? And that's it is not unintuitive. It is just the more mathematically precise way of saying what we intuitively understand. Okay, but you have to be a little careful. Okay, that's the formal definition of this construction. It's called subset construction. Why? Because my set of states are the subsets of the states of the power set of the old NFA, right? Okay. Okay, that's the formal definition. Here is an example. Okay, no epsilon transitions to make our life easy. How many states should this DFA have? Is this an NFA? Okay, because on one it can go to two places, right? Okay, so here is the constructed DFA. Remember, it's automatic, right? This is a conversion from NFA to DFA. How many states are there? 4. Let's label the states. What are all the subsets of the thing? Empty set, okay, Q0, Q1, Q0, Q1, right? Those are all my states. What are the accepting states? Well, anything which has an intersection with an accepting state of the old DFA. So this one is accepting, that one is accepting. Yeah? Okay, now we have to figure out the transitions, right? Why does the empty set have transitions to itself on 0 and 1? If the NFA was in empty set, is not in any state, where can it go? It can't go anywhere, right? From the empty set, according to the definition, there is nothing to go to. There is no states. So it's an empty set. Okay. Okay. Why is it the case that on Q0 on 0 we went to 0? What is the definition from our construction? From Q0, we have to look at this machine and say, where could it go on string 0, right? Where can it go on string 0 from here? No? Okay, Q0, yeah, sorry, yeah. Right, the only possibility for this guy to go from 0 on string 0 is itself, right? So it's clear. But what about on 1? Where could this guy go on string 1? It can go to Q0 or Q1. That's why we went from here to Q0 and Q1, right? Okay, but what about Q1 itself? If I was in 0, where can I go? I can't go anywhere else, right? Okay, so that's it, right? So that is our understanding, yeah? Okay, let's do something a little bit more tricky. Okay, a couple of more minutes. So here this has epsilon transitions, right? Okay, now what are the, okay, so you realize here that these two states are not reachable from the start state, right? Yeah? You realize this, that these two states have no way to be reached by the start state. Are these useful? So we can get rid of them, right? Okay? So what we would like to do is only generate these two states and not get these states, right? If possible. Why is that important? Suppose look at this thing. How many states does it have? 4. But these are the only, so if you did the construction mechanically, how many states will it have? 16 states, right? It's very painful to do 16 states. But we see that these are the only 4 states that are reachable from the start state. So can we figure out an algorithm which only does this and not create all the 16 states and then figure it out? And yes, we can do it. How do we do it? We start with the start state. What is the start state of this machine? From definition, what is the start state of this machine? It is the epsilon reach of Q0, right? What is the epsilon reach of Q0? Q0 and Q1, right? So that is my start state, right? Okay. Okay, I start with that, and now I say, well, a DFA should have a transition on every letter, right? So where will this go on a 0? We go to this and say, how can we figure out what are all the states that I can go from Q0, Q1 on seeing the string 0? Okay, you go here and say, I could be either in Q0, Q1. I see the string 0. Well, I could be in Q3, right? And can I get to Q2 on seeing string 0 from Q0 and Q1? No, you cannot get to Q2, right? You cannot get to Q0 either, right? You cannot stay there with on a 0, right? And you cannot get Q1 either. So the only possible state from Q0, Q1 on seeing a string 0 is Q3. Okay, so that's how you construct the machine. So you only explore states as you create them. You don't create, if you run out of all states, I mean, if you don't create a new state, you're done, right? Because you're finished. And that's called the incremental construction, because you do it on a step by step.
Construction.
Yeah.
Because I think it's better to use x belong to q prime here.
No, it's not Q prime. Q prime is
X belong to q prime, the same thing, right?
no, yeah, you mean X belongs to Q. Yeah, sure.
Q prime.
Yeah.
Because it's clear to here because x has to be in the q prime, right? At first we
Yeah,
don't
sure,
have
sure.
this.
That's fine. Either is fine.
So I was wondering, when was the last day to sign up? That's
There is no last day per se, in the sense that